So a chord of a circle is a line segment whose endpoints are on the circle. So that means if I have a circle here, here's my center. A chord just means that it's touching two sides. It doesn't necessarily go through the middle. So all of these would be considered chords. It can go through the middle, that is okay, but it doesn't have to. So chords just touch two different, they have endpoints on the circle. So when you have two chords that are the same distance from the center, they are congruent. So if I have a circle with a center, and I have a chord, and I have a chord, and I know that the distance from here to here is the same as the distance from here to here, then what I know is those two chords are also congruent. So it says two chords, A, B, and C, D, are equidistant from the center. If they're equidistant from the center, that means the chords are equal. And 3x plus 7, AB equals 3x plus 7, and CD equals 27 minus x. Solve for x and find the lengths. So that means 3x plus 7 equals 27 minus x. I'm solving this for x. I want x's on one side, my numbers on the other. So I'm going to add x to both sides first. And that's a 1x. 3x plus 1x is 4x. Plus 7 equals 27. Then I'm going to need to subtract 7 from both sides. So 4x equals 20. And the last thing I'm going to do to get x by itself is divide both sides by 4. And x equals 5. So if x was 5, those chords would be congruent. So that's what can you say about two congruent chords in a circle? Well, if you have two congruent chords, then that means that they are the same distance from the center. So it's the opposite of what we said before. Before we said if they were the same distance, then they were congruent. Now we're saying if they're congruent, they're the same distance from the center. So given the information in the diagram below, you can conclude that AC, which is this one, is congruent to what other segment? Well, if I know this is 5.91 and I know this is 5.91, then that tells me that AC is the same as FD. If a radius of a circle is perpendicular to a chord, then it bisects that chord. So this here, what we have is in this 5.91, it told you it was perpendicular. So that means that it bisects FD. So FE is the same as FD. So this bisects. And that means that FE is equal to ED. So it says a radius of a circle OC is perpendicular to chord AB and intersects it at point M. So it's probably going to help us to draw a picture. So I have a circle with center of O. It says a radius of the circle OC, so OC goes from the middle to the outside, is a perpendicular chord of AB. So that means AB is here. And we know this is perpendicular. And intersects at point M. So this is point M. It tells us that AM is 45 minus 5x. And BM is 30 plus 10x. So find x and find the lengths of AM and BM. Well, we learned that if the radius is perpendicular, then it bisects, it splits this in half. So that means that 45 minus 5x is equal to 30 plus 10x. And I can solve for x. So I want x's on one side, my numbers on the other. So I'm going to subtract 45 from both sides. So I have negative 5x equals negative 15 plus 10x. Then I'm going to subtract 10x from both sides. So negative 15x equals negative 15. And then I'm going to divide both sides by negative 15. And I get x equals 1. So if x is 1, I can plug that in here for x. So 45 minus 5 times 1, which is that 45 minus 5, which is 40. And then we could check it. 30 plus 10 times 1 would be 30 plus 10 would be 40. So both of the pieces were 40. That did work out to be correct. So if a radius of a circle bisects a chord, what else must be true? Well, if the radius bisects it, then we also know that the radius is perpendicular. So if the radius OB is perpendicular to the chord AC, and we know that AB is 3.2, what is the length of the chord AC? So again, we have a circle with a center at 0, and we have a chord AC, and it tells us that OB is perpendicular. And we know that AB, this piece from here to here, is 3.2, so it asks us for how long is AC. Well, remember, if it's perpendicular, it bisects it, so if the top part's 3.2, the bottom part is 3.2, and then the whole thing would be 3.2 plus 3.2, which would be 6.4. The last question says, what is another name for a chord that passes through the center of a circle? So if I have a circle, here's my center. If a chord goes from one side to the other and passes through the center, that particular chord is called the diameter. The diameter goes all the way across. We talked about that a little bit in the last section. It goes all the way across. So question 1 says to name all the diameters. Well, diameters have to go through the middle, and they have to touch both sides. So HW would be a diameter, and FZ would be a diameter. Number 3 says the segment shown is a radius. What is the length of the diameter? Well, we know that a diameter is twice the radius. So all I have to do is 4.7 times 2, which gives me 9.8, and that would be my diameter. Number 5 says the segment shown is a diameter. What is the length of the radius? Well, if the diameter is twice the radius is half the diameter. So I have to take 26.6 and divide it by 2. 26.6 divided by 2 is 13.3. Number 7, if the dotted line segment is a radius of circle X and YZ is perpendicular to XY, XW, and YW is 4.5, what is the length of the chord? So we're going to look at the next page and look at the picture. We know that YW was 4.5, and the question asked us how long YZ was. Well, if I know this is perpendicular, that means that this part and this part are equal, so they're both 4.5. So to find the whole chord, I do 4.5 plus 4.5, which gives me 9. Number 9 says, what is the length of CD? Which is this piece right here. And what we know is that if these are the same distance, then this and this are the same distance as well. So CD would be 9.